All right. So we've got this problem about this 2 kilogram ball swinging on a string of length 80 centimeters. And just right now I'm going to assume that 80 is 2 sig figs, like 80 point. So what is the magnitude of the ball's velocity at position 2? Well, I've already set up this problem thinking about my system as the earth, the ball, and the string. Isolated system. Energy is conserved right here. In the beginning, there is some gravitational potential energy. I've defined y equals 0 as the position of the ball when it's at position 2. And that means there's some kinetic energy at position 2. And there wasn't any at 1 because it was released from rest. So, simply mgy equals 1/2 mv squared. M's cancel out, I'm not going to need them. Or v equals the square root of 2gy. Now figuring out that height involves a little trigonometry. But I can realize that that height is right there, that's y. L is the length of the string, which is 80. So this is just going to be the square root of 2 times 9.8 newtons per kilogram multiplied by 0.8 meters times the sine of 40 degrees. And that's going to give us our speed at position 2. We can do that right now. 2 times 9.8 times 0.8 times the sine of 40, and then the square root of that. So that is 3.2 meters per second. For part B, we are asked about the tension when the ball is at its lowest point. So swinging through like that. And immediately I can realize that the force of tension acting on this ball is going to be bigger than the force of gravity, because this ball is moving in a circular path, and it has an inward acceleration, that's centripetal acceleration. So the Newton's second law says A is equal to the sum of the forces acting on the ball divided by the mass of the ball. And the acceleration is v squared over r. I'll multiply the mass over on that side, all in one step, and the sum of the forces will be Ft minus Fg, defining in as positive. So then it's mv squared over r plus mg will equal the force of tension. Now I know the mass, I know the radius, which would be the full length of the string, and I know the gravitational field strength here. What I need is the speed, because the speed at point 3 is not the same speed at point 2, because this ball is a little bit lower, and since it lost some height, it's going to have some more speed. So I'm going to redo that whole energy problem just like right here. But it's gravitational potential energy turning into kinetic energy. And what I actually care about is just v squared. That's what I'm going to plug into my problem over here. And that is just equal to 2gy, where y is the full length of the string. Defining the place where y equals 0 is down here. The ball must have started one string length up. So that's 2 times 9.8 times 0.8. V squared is 15.68. That gets plugged in right there. Times the mass of the ball, 2, divided by the radius, 0.8, plus 19.6, the weight of the ball. And then I get my final answer of 58.8 newtons, or with 2 sig figs, 59 newtons. So ran out of space to make this problem nice and neat, but the steps are all there. Using the conservation of energy, figure out the speed or the speed squared in the case of position 3, and then using that value to figure out the force of tension, realizing that I have some centrifugal acceleration there. Great one to look at. Thanks for watching.